Hi all, I am K. Surya, working as Assistant Professor in the Department of ECE at SNS College of Technology. So in this video, let us see how PN junction diode works in the forward and reverse biased conditions. So first we will see the forward bias. So when the positive terminal of the battery is connected to the P type and negative terminal of the battery is connected to the N type of the diode, it is known as forward biased condition. So when the applied potential with the external battery acts in opposition to the internal potential barrier and it disturbs the equilibrium. As soon as an equilibrium is disturbed by the application of an external voltage, the Fermi level is no longer continuous across the junction. So when you apply a voltage, the applied potential repels the holes in the p-type region. So the holes will start moving in the opposite direction towards the junction. Similarly, the negative potential will repel the electrons and the present in the n-type region, and it will move in the opposite direction towards the p-type region. So eventually, when the applied potential is more than the internal barrier potential, the depletion region and the internal potential barrier will get disappeared. So when the p-type and the n-type holes and the electrons move towards the opposite regions, the depletion region will get reduced. So this is the characteristics of the PN junction diode during the forward bias. So as Vf is less than V0, the forward current is almost zero because the potential barrier prevents the holes from the P region and electrons from the N region to move between the to cross the depletion region in the opposite directions. Once the current voltage is reached, then the current will start flowing. So when Vf is greater than V0, the potential barrier at the junction completely disappears and hence the holes cross the junction from P type to the N type. So the electrons across the junction in the opposite direction, resulting in relatively large current flow in the external circuit. Say a feature worth to be noted in the forward characteristics is that the threshold or the cut-in voltage below which the current is very small. So it is 0.3 for germanium and 0.7 for silicon. So at this cut-in voltage, the potential barrier is overcome and the current through the junction starts to increase rapidly. Next one is the reverse bias condition. So here you will be connecting the negative terminal of the battery to the p-type region and positive terminal of the battery to the n-type region. So this causes the reverse bias. So under this reverse bias conditions, holes will form the majority carriers of the p side. It will be moving towards the negative terminal of the battery and the electrons will be moving towards the positive terminal of the battery. So width of the depletion region will get increased here. So thus the electric field produced by the reverse bias voltage is in the same direction as the electric field of the potential barrier. So the resultant potential barrier is increased, which prevents the flow of majority carriers. So depletion width will be proportional to V0 power 1 by 2 under the reverse bias. So no current should be flowing in the external circuit. But in practice, a very small current of the order of a few microamperes would flow under the reverse bias as shown in the figure. Electrons forming covalent bonds of the semiconductor atoms in the p and n-type regions may absorb sufficient energy from heat and light to cause breaking of some covalent bonds. So the electron hole pairs are continually produced in both the regions. Under the reverse bias condition, the thermally generated holes in the p region are attracted towards the negative terminal of the battery and the electrons in the n region are attracted towards the positive terminal of the battery. Consequently, the minority carriers, that is the electrons in the p region and the holes in the n region, wander over to the junction and flow towards the majority carriers side, giving rise to a small reverse current. This current is known as the reverse saturation current I0. So the magnitude of the reverse saturation current mainly depends upon the junction temperature because of the major minority carriers is thermally broken covalent bonds. For large applied reverse bias, the free electrons from the n-type moving towards the positive terminal of the battery acquire sufficient energy to move with high velocity to dislodge valence electrons from semiconductor atoms in the crystal. These newly liberated electrons in turn acquire sufficient energy to dislodge other parent electrons. Thus, a large number of free electrons are formed, which is commonly called as avalanche of free electrons. So this leads to the breakdown of the junction, leading to a very large reverse current. So the reverse voltage at which the junction breakdown occurs is called as the breakdown voltage. Hope you understood how the PN junction diode works in the forward and the reverse bias situations. Let us take up some few assessment questions. So if the positive terminal of the battery is connected to the anode of the diode, then it is known as, the options are forward bias, reverse bias, equilibrium and Schottky barrier. Yes, the answer is forward biased. During reverse bias, a small current develops which is known as, the options are forward current, reverse saturation current and active current. Yes, the answer is reverse saturation current. If the voltage of a potential barrier is V0, a voltage V is applied to the input, at what moment will the barrier disappear? The answer is V is equal to V0. Thank you for watching this video.